Hello all, my name is Himani and today I'll be sharing our work on MorphMag, reconfigurable interfaces by shape change and embedded magnets. This work was undertaken by a dedicated team from Texas A&M University, KAIST, and National University of Singapore. The evolution of user interfaces has increasingly leaned towards digital solutions. However, physical interfaces remain indispensable, offering tactile feedback that digital interfaces can't replicate. These become important in contexts where multimodal interactions are expected, such as mixed reality or while you're driving, or even in cases of disabilities. The challenge then lies in the static nature of the existing physical interfaces. That is, they lack the flexibility to adapt to changing user needs without costly redesigns or modifications. Most of the current tangible interfaces available are either bulky to fabricate, requiring a prerequisite knowledge of electronics or embedded motors, or require refabrication and replacement of parts to be customized or reconfigured for a particular user. Our project seeks to address this by enabling real-time reversible shape changes in physical interfaces using embedded magnets and thermoplastic materials that can be easily fabricated using desktop 3D printers. We are inspired by works focusing on creating dynamic physical interfaces using various electronic and mechanical media, works that focus on geometric and printing control to characterize shape change and actuation, and works that enhance human interactions with tangible interfaces through the use of magnets to provide interaction feedback. I'll now go over our approach that combines wisdom from existing work and creates a novel space for reconfigurable interfaces. Firstly, thermoplastic filament has the ability to be manually deformed into new shapes when heat is applied. Here we use polylactic acid, that is PLA, which in addition to thermoplasticity has shape memory property, where on reapplication of heat the deformed shape reverts back to its original shape. The issue here is that the deformed shape change is hard to predict or replicate as the shape change forces are applied manually. To circumvent that issue, we also integrate geometric control where manual force can be applied to only specific parts of the geometry and the propagated force results in predictable and repeatable shape change. Then we embed permanent magnets into the geometry so that when heat and forces are applied, the embedded magnet is displaced from its initial location due to the geometry's changed shape, and this results in predictable and repeatable displacement of magnets in 3D space through shape change. This is the core concept that we utilize in creating reconfigurable interfaces. We will now go over the geometrical primitive that enables predictable shape change and how we use it. The geometric primitive consists of three parts: the magnet cell, which hosts the permanent magnet in the shape of a cuboid, the joints which form the thinnest parts of the geometry, and the edge cells, which are also in the form of cuboids. The parameters that can be controlled include the angle of the joint theta, its length L, and its thickness T. The idea here is that when heat is applied to the geometry, the thinnest part, that is the joints, will easily be able to deform. Since the magnet and edge cells are in the form of cuboids with their length to thickness ratio close to 1, deforming them is difficult, similar to how a solid cube or a sphere may be difficult to deform through manual force. So when heat is applied, in our case using hot water, we apply manual force to only the edge cells, either pushing them close together or pulling them apart in the same plane. This results in the force propagated through the joints to displace the magnet cell, which is our ultimate goal. By changing the different joint parameters, we can then predict how the embedded magnet in the magnet cell is displaced. We divide the displacements into three modules: vertical, horizontal, and angular displacement. When the joint angles are equal and greater than 0, we see vertical displacement of the magnet cell. When joint angles are both 0 degrees, we see a horizontal displacement of the magnet cell in the same plane. And when the angles are opposite, that is theta 2 equals 180 degrees minus theta 1, we see a twist causing an angular displacement of the magnet cell. Now that we know how the primitive geometry behaves, let's look at some topologies. We can combine the primitives to form other topologies. We explore two topologies, that is, the square topology with magnet cells at the corners and the spiral topology where primitives are all connected at one central point. But then, how can a user apply forces to multiple edge cells at once when multiple primitive geometries are combined? We add supports to each type of topology to assist in force application. For the square topology, other than pushing the two edge cells together similar to the primitive, we can also add a center pole connected to the edge cells so that it can be rotated to push the edge cells together. In this case, a stopper at the base can restrict the other degrees of freedom of the edge cells. So in this example, the stopper here has caused the edge cells to move closer, causing the magnet cells to undergo vertical displacement. In the case of a spiral topology, while we can add stoppers and have the same technique, we can also fix the outside edge cells and then either rotate or pull up the center pole in this case. In these examples, rotation can cause the magnet cells to move closer together horizontally altogether, or pulling up the center pole can cause the displacement of the magnet cells in a plane connecting the two edge cells horizontally. This brings us to our design space. We have seen the displacement modules, the controllable parameters, the topologies, the supports and user actions for reconfiguration. But what are we going to use this reconfiguration for? We believe there are two major areas where our techniques can be applicable. First, in customizing haptic feedback, and second, in reconfiguring interaction input motions. Let's start with haptic feedback. By moving the magnet away and closer to a base magnet, the feedback can be customized from continuous to discrete with increasing force feedback. As can be seen from the videos, initially the magnet cells are away from the embedded nuts in the base. After reconfiguration, the magnet cells move closer, causing increased feedback. Similar passive indicator can be attached to a sliding door of common space, and a user may indicate information to anyone entering by changing the feedback received when sliding the door. For example, high feedback may mean that a user inside is on an important call and not to make any noise when entering. Customizable force feedback can also be used in a rehabilitation device where a user with a lower grip strength may start with a lower feedback as seen in the videos and gradually move towards higher feedback as they regain their grip strength. This reconfiguration can be indicated by the medical professional based on the prescribed exercise. If a magnet is angularly displaced to orient away from a base magnet, it is equivalent to deactivating the magnet. This principle can be used to vary how many steps of feedback are felt in an interface. For example, in a video game controller for a fishing game, a user may want to feel all the clicks of the rotation when reeling in fish, as can be seen from the video. But when playing a driving game, the controller can be reconfigured to angularly displace two of the magnets to deactivate them, as can be seen here, resulting in only 2 clicks felt when turning the steering wheel to the left and right. We can also reconfigure input interactions. When we change the shape of the geometry, space is created around it, and that combined with the displacement of the magnets can result in different input motions. For example, a rotary motion can be converted to afford toggle motion simply through the deformation of the magnet cells as they move up and down. Such reconfiguration can be used to convert a twist to open door handle to a push to open door handle for users with wrist-related disabilities. Similarly, here when we move the base magnets to the cover with some space at the bottom, the geometry acts as a push button, moving back to the cover when pressed down due to attracting magnets. But when the center pole is pulled up, a dome shape is created which takes up the space that restricts the up-down motion and only affords a toggle or a joystick motion. Such reconfiguration can be used to create a toaster controller for safety. A push button may be used by children to perform pre-programmed settings, constraining them from using finer controls such as temperature or timer. But A healthy adult may want full control and they can reconfigure the controls to become a joystick where one motion can control the temperature and the other can control the timer. Let's move on to evaluation. We tested different joint angles and joint lengths and calculated the vertical, horizontal, and angular displacements. We see that by increasing equal joint angles, there is an increase in z displacement or vertical displacement, but after 45 degrees, we see some angular displacement as well, which may not be desired. Similarly, when the opposite angles are increased, we see the angular displacement increase with the increase in theta 1, but there is also some vertical displacement here. So we recommend keeping the maximum theta 1 to 45 degrees and calculating the opposite angle accordingly. The other changes then can be made in the length of the joints. As can be seen here, as the joint length increases, the vertical displacement also increases, but with the increase in the joint length, the angular displacement reaches a maxima. These values can be used by designers in creating their own such interfaces. We also tested if displacing the magnet cells from a base magnet causes difference felt in the force. For vertical displacement of magnets, where a magnet is moving closer and closer to the base magnet, this graph indicates that the force felt increases as the displacement increases. Similarly, in rotational reconfiguration, where the magnets move away from the base magnets, this graph shows that the force felt decreases as the displacement increases. And lastly, we evaluated the deactivation of a magnet cell through angular displacement. Without deactivation, we felt 5 peaks and 5 valleys, but after deactivation of one magnet, the felt peaks and valleys were divided to half. This validates our approach of using the magnets and the thermoplasticity for changing force feedback. Moving on to the discussion, limitations, and future work, we use hot water for heating our mechanisms, but in real-world scenarios, a sophisticated embedded heating mechanism would be required, as has been explored in related work and is still being studied. Secondly, we require manual force for reconfiguration, and while automation may be possible, reconfiguration is context and preference driven, and it is heavily dependent on the human using the interface. So just as a musical instrument is tuned to the preference and requirement of a musician, reconfiguration of interfaces requires a certain extent of human intervention. Beyond manual shape change, programmable shape change is also possible, but this technique uses the conflicting forces of shrinking caused by stresses released by the polymer in the direction of printed lines. So these objects cannot be unshrunk and would require further consideration in terms of mechanism and magnet sizes. Lastly, we have only looked at a few parameters of the geometry, and other parameters such as angle between joints, speed of recovery, etc. can affect the behavior of the mechanisms. Hence, as future work, we would be evaluating the rest of the parameter space and using the knowledge to further assess designers of such mechanisms. In conclusion, by combining the versatility of shape-changing mechanisms with the tactile feedback of embedded magnets, MorphMag offers a new way for users to interact with technology, one that is more intuitive, responsive, and personalized. Thank you so much for listening.